if you've done any search online on this topic, you know there's tons of information, and there's also tons of misinformation. And one of the things I wanted to assure you about tonight is that everything I'm about to say, I can back up with links from reputable sources, and certainly if you are interested in any of those, I can get those to you. Tonight we're going to be talking only about some aspects of fracking. We don't have time to get into some of the things that I'd love to get into, such as some of the leasing concerns, a little bit more of the politics. We'll go over some of the geology of the Marcellus and the Utica formations so that you can understand why gas companies are interested in New York State. We'll also go through the technological process of fracking, just the basics. And then we'll hit some of the impacts of fracking. Now, one of the things I'll tend to leave out is a lot of the good news, because you see those and you hear those on advertisements and through other sources. Certainly, fracking does promote some economic benefits. But what I'll try to give you are things that you will tend not to hear in the everyday media about fracking. Here's a map of New York State with the towns and counties shown. And right now, we have about 170 villages, towns, and cities in New York State that have enacted bans or moratoria on fracking. Why am I telling you this? Well, as you know, New York State has a de facto moratorium. It's been going on ever since David Patterson signed it into law several years ago. We're not sure how long that's going to last. Supposedly, there's a health study going on that was supposed to have been finished months ago, and they were going to base the decision on that. As far as where that health study is, it's up in the air. And so I think the message for us is that New York, as a state, could keep the moratorium on fracking for many more years, or we could read tomorrow morning that it's been lifted. And so from what I've read about fracking, I feel it's very prudent for municipalities to have some type of ban or moratorium on fracking as a second layer of defense, so that if New York does lift the ban or the moratorium, then the town or city or village is still protected. They can always lift those bans or moratoria, but once fracking starts, it's incredibly difficult to enact a ban or moratorium. So I would urge any of you, after you've seen this tonight, if you're interested in working with your town board or your city council or your mayors or your supervisors on bans or moratoria, see one of us that are here. We'll give you some information. We can give you sample language. We can direct you to lots of helpful resources. Okay, let's get started. First, I will list 9 things that are commonly said about fracking by the industry. First, there's over a mile of solid rock between the frack fluid and our drinking water sources, so it's impossible for chemicals to reach the surface. Chances are good you've heard all 9 of these before, or at least most of these. 2, there's no instance of fracking ever contaminating groundwater. 3, fracking will greatly increase the economic prosperity of the region. 4, fracking will allow us to become energy independent, so we won't have to rely on those unstable Middle East countries for our energy. 5, shale gas is the cleanest fossil fuel, and it will be a bridge fuel for the U.S. as we transition to renewables. 6, we've been fracking since 1947 without major problems, so why all the fuss now? 7, the Marcellus and Utica reserves will last us 100 years. 8, the chemicals are like those under your kitchen sink. And 9, New York State regulations, once they're in place, are the strictest nationwide and will ensure that fracking is done safely. I want to tell you unequivocally that every single one of those statements is true. Also, every one of those statements is false. And hopefully by the end of this evening, you'll be able to see the truth and the falseness in each of those. Well, let's start at the very beginning. So what is natural gas? Well, the nation's first natural gas well was dug by William Hart in, some people say 1821. Most of the sources I found said 1825, and it wasn't very far away. It was in Fredonia, New York. And he used pipes made out of wood and tin and lead, and he actually lit up some of the Fredonia buildings with the natural gas from that. So how did that gas get there? Well, up on the screen is a picture of what this area looked like about 400 million years ago during the Devonian period. At that time, we were covered by a shallow inland sea, about 300 feet deep, and there were some very strange creatures like the horn corals and trilobites and cephalopods shown. And further out, there was a lot of deposition going on. And because it was a tropical sea, just like today's tropical seas, there were also a lot of microscopic organisms, phytoplankton and zooplankton, and little krills and things like that, very small organisms that had a lot of biomass. They had a lot of hydrocarbons in them. And what was happening at that time was, if you've been out to New Hampshire or Vermont, you know how high the Green and White Mountains are now. Well, back then, they were higher than the Rockies. And you had great rivers that were carrying the sediment from the erosion of those mountains out towards the sea, where we are. In fact, any of you that have been to Panama Rocks or places like that, those big white quartz pebbles that are in that, they used to be out in New Hampshire. That's where they were originally eroded from. Out in the area we're talking about, a lot of clay particles were being deposited. And so as these little plankton and things died, they settled to the bottom, got covered with clay. And so what happened was, the hydrocarbons were trapped in that clay. And then as layer upon layer built up, through the heat and pressure, through the heat and pressure, they got cooked. And very slowly, that organic material turned to oil, and then to gas. And then eventually, if it's cooked too long, it essentially disappears. And as far as human use, isn't very marketable. But the problem with this is, because clay is such an impermeable particle, especially once it's compacted into shale, the gas that's in there is it's what we call tight. It's very hard to get out. It won't come out by itself. But I'll explain how we figured out how to get it out. It took hundreds of millions of years for this gas to form. I think you realize it only took about 1.5 centuries for humans to burn most of it up. There isn't that much left compared to what we started with, at least not very much readily accessible. And what we call our conventional deposits of both oil and gas were and are being severely depleted. So back in 2008, when Terry Engelder from Penn State and Gary Lash from SUNY Fredonia did some estimates about how much gas was in the Marcellus shale, and they had estimated that there were over 500 trillion cubic feet. Now, the law of extraction says you typically can get about 10% of that out. So even at 50 trillion cubic feet, that's still worth about $1 trillion. So the gas company was pretty excited at that point. So what is it about the Marcellus and Utica layers that make them so appealing to the gas companies? To look at that, to find that out, we need to do a little bit with some of the Marcellus and Utica geology. First of all, that's a geologic cross-section of the area. And we have the Marcellus formation out of the two that we're looking at being the younger of the two, and so it's closer to the surface. It's Devonian, and you can see the Utica is much lower. It's Ordovician. It's lower and it's older. Now notice there's a third arrow that I've put in. This is the Medina sandstone, and that'll be important in just a minute. But if you can remember where that was in the column, we'll get right back to it. Back to the Marcellus for a second. If you take a look at the Marcellus depth map, you'll notice that beneath our feet, it's about 3,000 feet. And then as you go more towards Pennsylvania, Binghamton area, it gets deeper and deeper. If you look at the thickness, it's kind of a similar story. It gets deeper towards the Binghamton and northeastern Pennsylvania. But in this area, you notice that the Marcellus is only about 50 feet thick. So because of that, if you have gas company landsmen coming to your door asking to lease your land, if you ask them, they're probably not all that interested in the Marcellus. 50 feet is too thin to be economically viable, at least at the prices of today and likely future prices. However, if you look at the Utica, you notice a couple of things. One is because it's older, it's deeper. It's about 5,000 feet deep under our feet where we are. And also, if you look at the thickness, you'll see that it follows the same kind of pattern pretty much that the Marcellus, but in our area it's about 250 feet thick. That makes it where it could be economically viable. Different than the Marcellus, it's much more uneven. The Utica has much more in the way of sweet spots and sour spots, where the Marcellus is a little bit more even as far as when you drill down to it, you know pretty much what you're going to get. The other thing that you should be aware of for the geology is something called wet gas and dry gas. If you remember before, I said that the longer they're cooked, they go through this sequence of different stages, and because of the depth that they're at, that cooking rate changes. And so if you look out towards the west, you see that black band, which is immature. It hasn't been cooked enough, even though it's very, very old. And then as you get further east, you'll notice that we get into oil, and then we get into wet gas, then we get into dry gas, and then the yellow is overmature. It's been overcooked, and the hydrocarbons aren't useful for humans at that point. So what's going on right now? Well, a couple of things. One is that there had been a big flurry of drilling in Pennsylvania, and any of you that have been down there lately know that you don't see as many trucks as you used to, and if you do the reading, you'll find out what happened was, because of some overproduction, the price went way down, and now a lot of those drillers are out in Ohio drilling oil instead. The other thing you should be aware of is this wet gas, dry gas difference. Wet gas means that it has high levels of what are called NGLs, which are natural gas liquids. These are things like, well, first of all, you know that natural gas is mostly methane, right? The NGLs, natural gas liquids, are the things like propanes, butanes, ethanes, lots of those kinds of things, pentanes, the ones that they use for camping fuel, for plastics, making your sandwich bags, etc. And wet gas typically sells for about twice as much as dry gas does. So people that have wet gas, and in Chautauqua County it's only on the very edge over by Dunkirk, just before you get under the lake. If you have wet gas, it's definitely worth more than dry gas, just to be aware of that. So how have we extracted this before? You hear that, well, we've been doing this since 1947, and that's true. The process called fracking, which I'll describe in a bit, has been done since the 40s. But the way we always did it was in the context of what we call conventional drilling. And this slide shows conventional drilling. You have a drill rig, and it drills a vertical bore down to one layer, and that layer in our area typically is that layer I talked about before, the Medina sandstone. And because the sandstone is a very permeable rock, when you drill your bit into it, you'll be pulling gas up, and then just like a water well, the gas can flow in from the sides through the permeable sandstone, and it will keep feeding your well bore for years and years and decades, actually. Because of the permeability, one vertical well can access an awful lot of gas that comes in through the sides, and it will go on for decades. This kind of drilling uses some water, typically a couple 100,000 gallons per well. I know it sounds like a lot, but wait till you hear the rest of the story. And it uses very, very little in the way of chemicals. But those kind of wells typically were fracked. In fact, some of your own water wells were fracked also. Fracking simply means that we shatter the rock around the end of the well so that it increases the permeability, and whatever it is we're trying to get, whether it's water or gas or oil, has an easier time flowing into the well. And the way it's typically fracked, at least for gas and oil drilling, is actually using perf charges, explosives, and that will perforate the well casing and will help to crack the rock. But a lot of it occurs when they use high pressure fluids that open up cracks that are already there, naturally occurring fractures. And we'll talk about that in a bit. So that's the conventional type. The horizontal drilling starts out with a vertical well, as you can see on this one. And then what happens is they can turn the well, as they're drilling it, they can turn it sideways so it goes laterally along the formation. So even though we usually call it horizontal drilling, it's really lateral drilling, because that formation that we're targeting might not be perfectly horizontal. It might be at a slant, so we drill along it. And what's cool about this method is that they can access very thin layers, and when they go to horizontal, they can drill up to 2 miles that way. Typically, it's only about a mile, but they can go up to 2 miles. And so with that one well, even though it's a very thin layer, because they're going horizontally or laterally, that can access an awful lot of rock that if they were only drilling vertically, they wouldn't be able to access. Horizontal drilling, along with the other things that I'll talk about, was first done in the Barnett Shale down in Texas in 1997, and then in our area, in the Marcellus, some people say 2003, some people say 2005. Either way, it hasn't been very long. Most fracking wells, the kind that we're talking about for this controversial topic, most of them are just a few years old. Certainly not decades old, like some people say. So here's a close-up of the horizontal section, and what they do is they start at the end, they block off section by section, they lower explosive charges through that, and basically perf the casing, and if they're drilling in a small, narrow layer, they'll shape the charges so it goes mostly out to the sides. And they're very good at doing this. They use little microseismometers to figure out how far the little fractures are going. And generally, they can do this pretty precisely. There are some cases where the frack has gone outside of the target layers, in fact, as much as 500 meters outside, which isn't good. That's a pretty big blunder, but that usually doesn't happen. So as far as the fracking process itself, it's not that environmentally dangerous. You're shattering rock typically close to a mile below the surface. And at that point, there isn't much environmentally that people would raise much concern with. The other thing you should know is sometimes you'll see frack or fracking spelled without the K. The industry usually doesn't use the K, just to be aware of that. And this process that I'm talking about is called HVHF, or high volume hydrofracking. And it's called high volume because of the amount of water that's used, and I'll explain that in just a minute. Here's what a typical setup would look like. The surface, you can see 4 white spots. Those are the well pads. Typically, the well pads are about an acre or so in size, sometimes up to 2 acres. And each well pad can hold several wells, up to 12 typically, but usually it's only about 6. And in this diagram, it shows 6 wells. I think you can see that coming off of each of those well pads and going down and then going horizontally. And then those fuzzy white caterpillar-like things are the horizontal sections that have been fracked. So you can see that just by using 4 well pads and not taking too much surface area up, they can frack that's probably close to 4 square miles shown on that. So here's the way they do that. They do, as they're drilling down, they lower in pipe to help contain any material that might be in the rock layers that they're drilling through to make sure that doesn't get into the well casing itself. And they start out with very big pipe, typically 2-foot diameter pipe. And then as each section is done, they go smaller and smaller and smaller until finally they're down to about a 5-inch pipe. That's pretty typical for the horizontal part. As they go down section by section, they also do some cementing that I'll show you in a bit. But first, if you've never seen drill pipe before, here's 20-inch pipe. And then here's some smaller stuff, probably 5 or 5.5 or 6-inch production casing. And then at each section, because it would be very easy for the pipe itself to be compromised and leak, what they do in each section, after they've done each section, is they push cement, a very loose cement slurry, down to the bottom of the well, and then that comes up between the outside of the well casing and the rock, because the hole's been drilled a little bit bigger than the casing itself. And that area it comes up in is called the annulus, and they have to do this part pretty perfectly. Because if they don't, it's very easy for materials that are at any layer, any elevation down in the rock to get into the piping or follow the edge of the piping up to the surface. So whether it's an aquifer and water or whether it's nastier stuff from down below, they have to make sure that they perfectly cement each one of these sections. And we'll talk about how perfectly they do it in just a little bit. Okay, so back at this. Once they have drilled down and fracked the well, they hook up some very, very large diesel pumps. That's shown in the lower right-hand picture. And they hook these things up together, and when they fire them up, typically it can produce about 9,000 or 10,000 pounds per square inch. And they pump fluid down into the well that they've just fracked. And the fluid typically has millions of gallons of water. You'll read typically 2 to 12, so 6 is about a reasonable figure for how much water it uses. Each well, not each well pad, uses about 6 million gallons of water. It also needs several, and I can't read what I wrote, what is that, 4 million pounds of sand? And the sand is used as what's called a proppant. The little tiny cracks that are formed will close up again if they reduce the pressure. So the sand gets in there and props the little cracks open, which allows the gas to flow more freely once they get the frack fluid out. Now, together, the water and sand make up about 98 or 99% of the fluid they put down there. The other 1 or so percent are chemicals. Typically about 120 to 440 tons of chemicals per well. Not pounds, but tons. That's a lot of chemicals. And so even though it makes up a very small percent, and even though it's very diluted, there's still an awful lot of chemicals per well. And if you multiply that times the tens of thousands of wells that have already been done, or the hundreds of thousands that they would like to drill, that adds up to a lot of chemicals. Before we leave this slide, I should point out on the lower left, that's what a pattern of well pads might look like so that they can access as much of the area of rock as they can. Each one of these is called a drilling unit and covers, well, typically it can cover an acre or more, and actually a whole drilling unit is several of these things to typically get 10 to 100 acres. It depends on which state you're talking about and which company and which formation. But that's the kind of pattern that it would follow. So what kind of chemicals do they use? Well, out of the 900 and something products that are used in the fracking, and when I say fracking, I mean the whole schmear from siting a well pad to completion. There's 900 and something products that are used, which contain 600 and something chemicals, some of which are at the top of the screen, but certainly not all of them. And the chemicals are used for things like biocides, surfactants, friction reducers, corrosion inhibitors. There's all sorts of different things they're used for. And certainly not all 600 and something are used in every single well. The geologists and the engineers will figure out what the right cocktail of chemicals is to do what they want done. Now, with these chemicals, it's been found, according to Theo Coburn, a noted expert on water issues and biochemistry, at least half of the chemicals known to be present in fracking fluid are toxic. Many of them are carcinogens, neurotoxins, endocrine disruptors, and mutagens. But Coburn estimates that about 1/3 of the chemicals in fracking fluid remain unknown to the public. These are kept as trade secrets. Technically, if your own land is being fracked, you can go to the company and get the MSDS safety sheets for the chemicals. Technically, you can. One of the other issues that you should be aware of is in order to supply 6 million gallons or so of water to a well, it takes a lot of trucks. And in fact, about 1,200 truck trips just for the water. Now, I did a little math. New York is a lot like Pennsylvania as far as its potential for fracking. And as you'll see later, Pennsylvania, even though it's had a few thousands of wells drilled for this new kind of fracking, has a potential for about 200,000 wells. New York does also if fracking is allowed in the state. So if you take that and you do a little math, so if there's 6 wells per pad, that means you're up to 7,200 truck trips per pad. And then if you figure 200,000 wells, that's 33,000 pads. That's if they frack New York to the level that they would expect to over the next 50 years, you're talking about 238 million truck trips. Not that this is the biggest issue in fracking, it's not, but it's certainly something to be at least aware of. It's a lot of trucking. Once they've fracked the well, once they've done all the expansion and once they've pumped the fluid down, then they basically open it up because the proppant's there, they're ready to release the fluid. And so when they open it up, because of all the pressure that's down there and the pressure that it was under, you get a great, I don't know how else to say, you get a great regurgitation of fluid mixed with natural gas. And we'll talk about what happens to the methane that's coming out at that time. but you get a lot of this material coming back. Once that settles down, and it's mostly methane that's coming out of the well, they use collecting pipelines and they send it to compressor stations. Well, first of all, if it's wet gas, they'll send it to a processing station, because in order to pipe it, you need to remove the butanes and propanes and so on. But once that's done, they put it into a compressing station like the lower picture shows, and that will then compress the gas and send it into larger transmitting pipelines. And by that time, the compressor station will also add the odor to it that you're familiar with if you've ever smelled leaking gas, because before that, the gas is odorless. Now, most of the time, the methane, when they open up the well, the methane is just released into the atmosphere. And I'll show you in a little bit what that looks like. Some of the times, they do what's shown in the upper right. They flare the well. They light off the methane. And yeah, that's valuable stuff, but at that point, it's very difficult to collect it because it's mixed in with all the other material. So what's the problem? Just had to put a flaming faucet in there because I knew you all expected that. But what's the problem? I mean, gas companies are making millions. There are landowners that are making, thousands, tens of thousands, sometimes hundreds of thousands. The Pittsburgh airport made $9 million leasing their land for fracking. So a lot of people are making a lot of money on this, and that's not to be denied. But what are some of the problems that you don't hear about too much? Some of it is just when you have fracking moving into an area. In fact, I have a confession to make. I spend an inordinate amounts of time on Facebook, on pro-fracking Facebook pages, trying to find out the other side's arguments, because I want to find out, am I thinking right, or is there something more to this than what I found out? And one of the arguments I often get is that, well, everybody should have the right to do with their property as they see fit. The problem is, it's never just on your property. First of all, contamination, noise, all that, none of that adheres to property boundary lines. And certainly when you have several thousand truck trips coming onto your property, your neighbors notice some of that too. It's changed everything all right, says Pam Judy, a resident of Carmichael's. Her now unsellable dream home sits 780 feet downwind of 3 enormous gas compressors, which appeared in 2009. It sounds like helicopters in the backyard, she says. The fumes make me dizzy. My children get headaches and nosebleeds. I have hundreds and hundreds of those kinds of things bookmarks, contaminations, incidents, health reports. We don't have time to look at many of them, though. One of the other things you should be aware of is the political side of this. As you know, there are major environmental laws at the federal level, things like the Clean Water Act, the Clean Air Act, the Safe Drinking Water Act, and many more. In fact, there's about 7 major laws. And over a period of years, and especially through the Energy Policy Act of 2005, I don't know if you remember back when Dick Cheney met with a secret group of people, and they tried to find out who that group of people were, and the court said, no, he can keep it secret. Well, shortly after that, we got the Energy Policy Act of 2005, which for oil and gas exploration and production exempts parts of 7 major federal environmental laws, exempts the fracking for oil and gas from those 7 major laws. So there are things that are going on with fracking that would not be allowed for any other industry. Pretty much every other industry has to follow all of those regulations, but fracking doesn't have to follow some of those, and that's why they can inject all those chemicals into the well without some very, very extensive and fancy permitting process. That's why they can do it as a matter of course. That's also why we're getting, and I'll talk more about this later, why in New York State we're getting frack waste from Pennsylvania that's setting off radiation alarms at our landfills. These laws, because they don't apply, they end up being some pretty good loopholes. In fact, this whole thing is known as the Halliburton Loophole. Now, it is true that states put their own additional regulations on, but even so, number one, it's a patchwork. What Pennsylvania does is different than what Colorado does, different than what West Virginia does. Not only is it a patchwork, but there are still some loopholes big enough to drive 1,200 tanker trucks through, for sure. So here are some of the issues that I'm going to be talking about tonight. And let's start with well casing seal leaks. We talked about how they have to be very careful cementing that annulus between the well casing and the rock. Unfortunately, that's a very, very difficult thing to do. And even though the industry, I'm sure, has incredibly cool technologies to do this and are using some of the best practices, these well casing seals have a ridiculously high failure rate. This graph is from the industry itself, from Oil Field Review. And this is from 2003, but if you check current data, it's pretty much the same, as I'll talk about. What they found was that the well casing seals right off the bat had a failure rate of about 5%. So about 5 out of 100 failed immediately. And then as they aged, they failed at a greater and greater rate. So by the time you get to 30 years or so out, about 60 of them had failed casing seals. That's a lot. And if, when a study was done to take a look at more recent things since 2003, the last 3 years, 2010, 11, and 12, the rates were actually higher than those 2003 rates. So either the technology isn't improving, or more likely because fracking, you know, we're talking about the quality of fracking, but it's the quantity of fracking. It's not just a few wells, it's a very big rush to expand this process as much as possible. There's probably a lot of slipshod work going on because, as we'll find out, the oversight just isn't there. What else could explain those very high well casing seal rates? So that's one of the environmental issues. And so what happens when a well casing fails? Well, sometimes you'll see it as bubbles of methane coming up right at the wellhead. But it doesn't have to fail all the way to the top, because all you have to do is get it where some of the gas or liquids can travel up, because then they can intersect natural fractures and joints in the rock and go laterally. And so as a result, a lot of people have had their water wells all of a sudden get a lot of methane in them after gas drilling. And that's what happened. It followed natural cracks over to these people's water wells, and it got in it that way. In fact, Duke University did a study, mostly in northeast Pennsylvania, but up into New York, where they did water well sampling, and they found some very interesting results. If you look at this graph, it's pretty direct correlation, where on the x-axis, on the bottom, if you look at that, this is distance to the nearest gas well, so it's really close and then further away. And then along the y-axis, it's methane concentration going up as you get higher. And if you notice that if you're far away from gas wells, your wells don't have much methane in them, if any. That's all these things down here at the bottom. Now, some really close also didn't have much. But if you look at the general trend, I think you'd all agree, if you had to draw a line on this, it would be that kind of a line. That as a drinking water well is closer to an active gas drilling well, the concentration of methane increases in that drinking water well. Now, can you prove that it's the fracking in the drilling? No, you can't. But I think anybody with some common sense, when you see that kind of correlation, it's pretty hard to explain it in any other way but that. But yeah, if you're a geologist or a scientist looking at that, you would not make the jump and say, well, gas drilling is absolutely positively responsible for this methane pollution in the water. You can't say that. But you can certainly think it, looking at this. Another important environmental impact of the whole fracking process is methane leaks. Remember we talked about that big regurgitation that happens when they first open up the well? Here's a picture of that taken from really quite far away. This is a false color image taken with a special camera that can actually see methane. And these purple things down here at the bottom are trees. So that's a tree line. That gives you a hint as to how big this release is. We can't see it when it's happening, you know, in real time, in real life. But with one of these cameras, you can see how much methane is actually released. So a lot of methane goes into the air, only about 15% of the time. Well, I should say this. As of a year ago, only about 15% of the time do they flare it off or try to collect it for sale. 85% of the time it just goes out into the atmosphere. I haven't found any recent numbers to find out how that's changed. It probably hasn't changed a whole lot, though. Flaring, you saw a picture of it before. Here's another picture. This will go on for several days, 24/7, very loud. Sounds like a jet engine is right next to you if you live anywhere near a well that's being flared off. I don't know if you've ever seen one of these in person, but they're pretty impressive. And to show how much flaring can be done, this is a satellite view of southern Canada, north central US. And you notice several cities on there, like Minneapolis, St. Paul, you know, they're glowing brightly in the night. But inside that circle is not a city. That's the Bakken oil fields up in North Dakota that you've probably heard of. North Dakota is doing very well economically because of those fields. They flare a lot because they don't have pipelines for the gas. They're more interested in the oil. So they just burn it off. And so at night, it makes that much light. There's that much flaring going on. It's a lot of methane lost. And methane is not only lost during that phase, even in the distribution. I think most of you are aware that our infrastructure is ailing quite a bit. And this is a picture of Boston, and each one of those yellow-green spikes is a big methane leak. We have pipes all over our country that are leaking methane. So methane use has led to many leaks from different phases of this, and we'll talk about why that's important later. Okay, if we go to the next section, flowback treatment, the liquid part of that regurgitated material that comes back is called flowback, and it contains all the stuff they sent down there. It also contains different elements and compounds that were down in that rock that it dissolved or pulled up with it, and it can be particles, it can be actually materials in solution, but it includes heavy metals like arsenic and barium. Also, as we'll find out later, it includes a lot of radionuclides. The black shales are notorious for being radioactive. So what did they do with that flowback? Well, first of all, as far as the numbers go, about 15 to 60%, it's highly variable, of the stuff they put down comes back up. And so if you do the math, obviously that leaves 40 to 85% of it still down in the well. So that means at minimum it's about 2.5 or so million gallons of toxic water that's left down in the well. We'll talk about why that might be a problem in just a few minutes. But the flowback that they do pull up quite often is kept in lined pits, like you see here, plastic lined pits. And yes, they sometimes leak. In some states, they're requiring them now to keep them in closed containers, but so far not that many places do that. And then what do they do with this? Well, they're trying more and more to reuse it to frack other wells. The problem with that is it gets more and more contaminated with each frack, and it becomes less and less useful for that. A lot of this goes out to Ohio, where they use deep well injection, which they use for a lot of other industries too. And just like as a geologist, I would never do rock climbing where the rock looks highly weathered. In a similar way, I think the deep well injection is pretty foolish. We inject highly toxic materials, sometimes not all that deep, down into the ground, assuming that it's never going to go anywhere. And that's an assumption that I don't think can be safely made, especially not, you know, if we did it a few times, that's one thing, but when we're doing it hundreds and thousands of times, that's another thing. But a lot of the flowback fluid right now is disposed of through deep well injection. Some of it had been and is being sent to municipal sewage treatment plants, which are not really designed for not only treating the stuff, but even testing for the materials that might be in that flowback fluid. And in fact, some companies have been fined quite large sums for polluting rivers from the effluent that comes from these sewage treatment plants and flows into them. So let's get to that problem of keeping all that toxic material deep underground. And so we'll call this one migration of frack fluid. Now this is something you don't hear much about. Out of all the different environmental and health problems with fracking, this one isn't brought up too much. But in my mind, I think it's one of the most potentially important ones. Even though the chemicals only make about 2% of the fluid, still in a typical well it's about 120,000 gallons of chemicals. And even when they're diluted, as I said, they can pick up a lot of nasty materials from the rock itself. Now, that mile of solid rock that we hear about from the industry, if you've taken 9th grade earth science, you probably remember that when Africa hit us millions and millions of years ago, you know, in the continental drift process, that created a lot of regular joints. If you go to Chautauqua Gorge or just about any stream, you see these kinds of regular joints in the rock, right? You've all seen that before. Those were caused by the plate collisions. And then our whole area has been uplifted. You know, the rock that was above the rock that we stand on has been eroded away and uplift has occurred. And that reducing of the pressure also expands the rock and cracks it. That makes more irregular fractures. You can't really see it in this picture, but there are irregular fractures that are connecting the regular joints. The sum is that no rock is solid, especially in the Northeast. All rock has a lot of joints and fractures in it. So then the question is, well, will that allow frack fluid to migrate upwards? Sadly, no gas company has allowed or has done it themselves substantial monitoring to actually measure how fast that fluid might be coming up. The very best thing they did, the closest they did, was they took a well that was 8,000 feet deep. They found an abandoned well not too far from it that was 5,000 feet deep, and they waited 1 year and then took samples from that 5,000-foot well, and they said, oh, no frack fluid, must be not migrating. Well, all that you can assume from that is that frack fluid doesn't migrate 3,000 feet in 1 year. We really don't know for sure if that fluid might be coming up or not. There are some indicators that it might be. These fractures in the rock provide routes of upward migration, and this is a study by Tom Myers. It has been seen that methane gas upward migration can occur quite quickly, and the increased presence of the gas close to fracture zones implies that it is using the fractures as pathways upwards. Gas can move more quickly through the fractures, but liquid frack fluid, along with the brine that was displaced by the frack fluid, and that also contains heavy metals and radionuclides, can also likely migrate upwards. And so gas can move, he says, anywhere from a few years to maybe centuries. We just don't know for sure. The way he did his study was through a lot of computer modeling and hydromechanics. So the question is he right, or is it going to stay down there? Well, unfortunately, there was another study, this also by Duke University, though it's a different study than the one I had mentioned before. What they did was they looked at present-day shallow aquifers, and in 3 of them, and this is in the Northeast, I think it was in Pennsylvania, in 3 of them they found methane. They also found brine and other materials that were from the Marcellus, not from the Marcellus layer itself, but from that general vicinity, that far down. And they did testing to make sure it was thermogenic methane, which is the kind that forms down in the black shales, as opposed to biogenic methane, which is the kind that you'd experience, say, if you stood behind a cow long enough. The thermogenic methane shows that it was definitely from down in that region, and it wasn't just shallowly produced biogenic methane. And they did all sorts of chemical analysis, and they can conclusively say that that material that was down there at the Marcellus level found its way into shallow water aquifers, or shallow level aquifers. Now, how long did it take? We don't know. Likely it took thousands, hundreds of thousands, maybe even a few million years. But I think the point is that if that could do it, then gases and fluids from frack fluids could also be coming up. But again, we need more study to find out for sure what the rate is. And if the joints and fractures aren't enough, here's a map showing some of the major faults in New York State. There are certainly more than that. And if you add to that the literally thousands and thousands of abandoned wells in New York State that we don't even know where they all are, you know, some of those could be pretty fast expressways to the surface for frack fluid. So that's still a pretty big unknown. So what does this amount to? Well, if you do the math for Pennsylvania, because that's already on its way, each square mile of shale will have 648 tons of chemicals injected into and staying in the shale, assuming 8 wells are drilled at about an 80-acre spacing, which would be pretty typical. So that's about 1 ton of chemicals per acre left below. they project that 50% of Pennsylvania will be drilled. So if you picture a map of Pennsylvania, half of that, a mile down, will be crisscrossed with fracks. So out of that 22,835 square miles, if you do the math, that ends up being about 14.8 million tons of chemicals emplaced under half of Pennsylvania. They are telling us that it's a sure, absolutely positive thing that that material can never move. Not for decades, not for centuries, not for millennia. I wish I could be that sure. I'm not at all from the studies that have been done. But I hope they're right. I really hope they are. Well, let's go to some other impacts. And I'm not going to spend too long on this because every industry has its accidents and spills and explosions. But this gets into that Halliburton loophole I talked about. This was in January near Roy Karen, Texas. What these guys were doing before the accident happened was they were transferring brine from one tank to another. That's what they call the flowback fluid, brine, because it is very salty. But it also has a lot of other materials in it. And unbeknownst to them, this batch had benzene in it and other hydrocarbons, volatile hydrocarbons. So as they were transferring this and they had left one of the truck engines running, all those volatile chemicals got into the air inside this open shed. And what happened, according to witnesses, was because this stuff is, is chemically a lot like vaporized gasoline, those truck engines that were idling revved up on their own because all of a sudden they had a lot more fuel in the air and backfired, and that caused an explosion. And ultimately, 3 workers were killed in this. If it wasn't for that Halliburton loophole, that truck could not have just been called brine, which sounds pretty benign, doesn't it? So there are certainly accidents and spills and explosions. Let's go on to some of the health impacts. What's been interesting, first of all, is some of the opacity. There's not a lot of transparency in all this, but the doctors that have reported in, the symptoms are pretty much the same wherever you go throughout the country for this. In fact, they have a name for it now. It's called downwind syndrome. It's usually a bunch of respiratory, neurological, and dermatological problems due to some of those chemicals that are listed and others. And more specifically, the symptoms are listed along the left. So these are pretty common for people that live near well pads, downwind of them, and people that live near compressor stations as well, because compressor stations put out a lot of things into the air. They're not containing all the material. And then there was a study done by Michelle Bamberger and Robert Oswald that found they were looking at more of the livestock and pets. After interviewing pet owners, farmers, and veterinarians, a wide range of drilling-associated ailments in animals, very similar to what the humans had, vascular, respiratory, reproductive, immunological, neurological, gastrointestinal, dermatological, and others, including sudden death within an hour of being exposed to frack fluid. A more recent study by Cornell looking at the impact on livestock and animals, after doing their study, they called for a ban until these things could be studied further. They were alarmed enough. Some of us in the room were down at the Blue Heron Festival this summer manning our anti-fracking tent, and some people from Pennsylvania came by and told us about a farmer down there that used to have an easy time selling his milk until they started flaring near his barn. And after reports from problems that other farmers were having, he had trouble selling his milk. Not necessarily because there were toxins in the milk, but because there have been so many other cases where there had been. So certainly the effect on agriculture as well as human health, so much of this really needs to be studied more and more. There's things getting in the way of some of those studies, though. For instance, in Pennsylvania, a law was passed making things called gag orders the law of the land, which means that if you're experiencing some of these symptoms in Pennsylvania and you go to your doctor, he can't tell you what he thinks is causing that. Now, he can, under the law, go to the gas company that might be drilling near you and say, hey, what chemicals are you using? And they are supposed to give him a list. he is under orders not to divulge that list, not to patients. He can't even call up other doctors to get their opinions on this. If he knows of another doctor that has a patient with similar symptoms, he can't say, hey, here's what I found out. So gag orders, especially in states like Pennsylvania, are quite problematic. And in fact, in that very same law, and as a former high school teacher, this kills me, that very same law, like down in Pennsylvania, you can see a schoolyard with a fence, and right next to the fence, you'll see another fence surrounding a drilling pad. They drill quite close to schools and other places where people live. And that same law exempts the gas industry from telling the community people, the fire department, EMTs, town officials, what chemicals they're using. They don't have to release that information. So there's some negatives with some of the health. And again, I'm just touching the surface on a lot of different topics here. One is that radioactivity I talked about, that the black shales are known for being radioactive. And in fact, if you take a look, this is an old-fashioned one. The more modern ones are much prettier, more colorful. But that's the way that they tell where the Marcellus and Utica shales and other black shales are down in the well. They essentially lower a Geiger counter and do a gamma ray count, and areas where it spikes, they know that's where the black shale layers are. So these things are notorious for being much more radioactive than typical rock. And because the drill cuttings and the frack fluid brings up that radioactivity, it's becoming more and more of an issue. Pennsylvania is in the midst of a study on radiation problems with fracking. Ohio has experienced this. As I mentioned, some frack waste comes up and goes into 5 different landfills in New York State, and radioactive isotopes are a problem with that as well. Another thing that happens is that frack fluid, because it's so salty, is sometimes used and spread on roads. Towns pay a lot for salt in the winter. I don't know if any of you are highway department folks, but when they find out that they can get essentially salt, even though it's in liquid form, at a much cheaper rate, a lot of municipalities go for that. New York State, well, first of all, let me talk about it in other states. In other states, that same frack fluid, and it's 8 times saltier than normal ocean water, so there's plenty of salt content, gets sprayed on the roads in the winter as a de-icer, also gets sprayed on dirt roads and gravel roads in the summer to keep the dust down. The problem is that material, as I said, has things like arsenic, barium, other heavy metals, and it also has radioactive particles in it. And so what happens is, I mean, as you know, your skin protects you from a lot of radioactivity, but if you're in a car, there's another car ahead of you, and that's kicking up dust, and that dust comes in through your car window or something, and you inhale that, where the skin might have protected you before, now you have that inside you. And that could cause cancers, decades down the road. So, I mean, there again are laws preventing this in other industries, but it's not happening with this industry. New York State has permitted this to happen. However, if you check with the DEC, they will claim that no out-of-state frack fluid is allowed. So that means they would only use frack fluid that was produced in-state, which means from the old kind of fracking, which should be a lot better because it's not going down into the Marcellus. It's typically going down into the Medina and other formations that aren't black shales and so shouldn't be as radioactive. That's an interesting thing to track down. And one of our projects for Cattauraugus-Chautauqua for clean water is going to various highway departments with our Geiger counter and seeing if we can find anything, because it would be a simple way to check them. One of the other problems, and again, I can only briefly talk about it, but I have hundreds of sources of information for this, is I think you realize that institutions like the FDA and some other ones that used to protect us from a lot of things don't protect us as well anymore. And the same thing is true for the EPA and Pennsylvania's DEP and New York's DEC. Some of this is through absolutely no fault of their own. Budgets get slashed like anything. They simply don't have the manpower to do this. But there seems to be a more insidious side to this as well. For instance, the EPA out in Pavilion, Wyoming, several years ago, did some studies, and they concluded, as in conclusively concluded, that fracking had contaminated the Wind River aquifers. Just a few weeks ago, and then they started doing a much more intensive study. Just a few weeks ago, they drop that study. And this has happened at least twice before in some major studies where they were hot on the trail and they dropped the study. So it seems like, and this is conjecture on my part, certainly I don't have proof, but it seems like they're getting pressure from somewhere not to be as investigative as they might be otherwise. So it's certainly something, again, I'm not pointing fingers at this point, but it's certainly something to be aware of as a possible problem with this. Okay, let's get on to global climate change. All that methane that's been released, one of the statements I read at the very beginning said that natural gas is the cleanest fossil fuel. Well, that's true if you're talking about just burning it. But if you take all the methane leaks and all the other problems with the extraction and processing and distribution process, it's not so clean. And in fact, especially with the methane leaks, that's contributed a lot to anthropogenic climate change, global warming, essentially. If you take a look at how much humans have put into the air, this is a graph from the last 10,000 years or so. And you can see just recently, and the recent part's been expanded to this, just recently the methane concentrations in the atmosphere have climbed. Now, is it true that nature adds methane to the atmosphere? Absolutely. However, if you look at the total methane added to the atmosphere by all the sources, the human sources are by far the biggest. That's what this pie chart is. Something like 61% of the methane is from humans. And of that, the gas and oil industry is 37% of that. They're the biggest chunk of that pie. They even beat out cow farts. So it's a pretty big source of methane for the atmosphere. And one of the things about methane is even though there's much less of it in the atmosphere than carbon dioxide, so a lot of people don't consider it to be as big of a threat. However, a methane molecule is typically 25 to 105 times more potent as greenhouse gas than a CO2 molecule is. And it depends on the length of time that it stays in the atmosphere. But certainly if you combine the methane and the carbon dioxide that we've added to the atmosphere, the nitrous oxide we've added, and there's some other greenhouse gases as well. Nobody can deny that we've added an awful lot of methane along with carbon dioxide to the atmosphere. So now we get to the culminating question. Is fracking safe, or does it pose a risk to the environment and our health? That depends on the way you look at things. Let me read you this account. When several unrelated patients visited Amy Perret, a McMurray, Pennsylvania doctor, she initially was unsure what to make of the bleeding, oozing lesions covering their faces. The wounds were not cancerous, but the inflammation was severe and becoming worse. Dr. Perret's suspicions grew when she learned that the patients all lived near the same natural gas drilling site. Tests later found that the patients had phenol and hyperic acid in their urine, two contact irritants rarely found in humans, but which were used in the gas wells. The patients improved after they stopped drinking water from their underground wells. Now, to most people, and probably to most of us in this room, that's enough information to suspect that something in the drilling is causing their illness. But again, can it be proven? No, it can't. Some of you that are old-timers like me remember when nuclear fuel services came into the West Valley area. And not too long after that, we started seeing an increase in birth defects. Quite a while after that, we saw an increase in cancers and some other illnesses. Can never prove that it was the radiation that caused that. But certainly to most people, that would raise enough red flags that they would take care of that. And fracking has definitely been shown to contaminate water wells, surface waters, the air, all sorts of things, and it's quite likely that it's the cause of at least some of this illness, both in humans and animals.